Happy Mole Part 2. We are looking at mole calculations whenever we have a solution. So recall that a solution is a homogeneous mixture. So that means when we look at it, it's all going to look the same no matter what part of the sample we're examining. All the properties are the same. Solution concentration is expressed in molarity. So concentration is how strong it is. It's like weak lemonade versus strong lemonade. Weak lemonade has a low concentration, whereas our strong lemonade, lots of lemonade dissolved in it, is going to have a higher concentration. So molarity is the number of moles of solute per liters of solution. So we see that formula there, big M molarity equals moles of solute divided by liters of solution. Molarity is going to have units of big M for molarity. We could use moles over liters, or also moles times inverse liters. So that little -1 just means as inverse, it's the same as 1 over liters, but another way that might be expressed. So we've added to our molar roadmap that we had. We learned how to get from moles to mass using molar mass. We've looked at how to get from moles to number of particles using Avogadro's number. Now we can also get to solution volume using molarity. So we're going to look at a couple different ways to do this, but by definition, molarity is going to tell us that 1 liter is equal to so many moles of the solute, and just like with molar mass and Avogadro's number, this statement of equality can be turned into a fraction and become a conversion factor. So let's start going through those examples. Again, if you're feeling confident with this, do the examples on your own and check your answers. You're going to get better practice. You're going to remember it better. It's just going to be better. If you need to go through it together, please also do that. Looking at some examples, and again, anytime we do examples in these videos, I hope you pause the video and take the time to try these out on your own before continuing on. That's just going to help you with your learning process throughout this year. So, example number 3 here. We're preparing a solution by dissolving 48.5 grams of magnesium bromide in enough water to make an 800 milliliter solution. We're looking for the molarity of both of those ions that make up our magnesium bromide. So let's start by thinking about what molarity is and what we need for that. So molarity is moles over liter. Anytime we use these brackets here, that means the concentration in molarity of the substance that is within it. So in this case, the MgBr2. Sorry, the Mg2 plus. So we need the moles of that Mg2 plus over our liters of solution. Well, to find the molarity of that Br minus, we also need its moles over the total liters. So again, our molarity of Br minus will be the moles of Br minus over the liters. Well, what do we know so far for moles or liters? Oh, we know how much solution we're going to make. We know our milliliters. We can change milliliters to liters real quick, just dividing by 1,000 or moving that decimal back 3 times. So our total volume of solution is going to be 0.8 liters. I want to make sure we keep those 3 sig figs, so 0.800 liters. Okay, so that brings us to needing to find our moles of these 2 ions. Well, the only other piece of information I have here is my grams, but we know how to convert grams to moles, so let's go ahead and start there. From our 48.05 grams of the magnesium bromide, we can get to moles using molar mass. So my grams are going to need to go on bottom, and its molar mass from the periodic table will equal 1 mole. So we're going to add up that 1 magnesium, 24.3, plus our 2 bromides, 79.9 for each of those guys, which should give us a total of 184.1 grams per 1 mole of the magnesium bromide. But I don't want moles of the magnesium bromide, I need moles of each of my ions. Well, this just comes from using the ratio of these ions within our chemical formula. for every 1 mole of MgBr2 that we have, there is 1 mole of magnesium ions. I know this because looking at the formula for MgBr2, there is just 1 magnesium within it. So every individual MgBr2 has 1 magnesium, so we're going to have the same number of both of those. So we can go ahead and stop here and solve because we've gotten those moles of Mg2 plus that we want. Keep our 4 sig figs here, and now that we have our number of moles, we can go plug that back into our molarity equation that we have. We plug that in and divide by our 0.8 liters, we end up with our 0.326 molar magnesium ions, and we do have to round that down to 3 sig figs. Okay, well, we still need our molarity of bromide ions, so we're going to need to go and find our moles of bromide ions. Well, we're still going to be starting with the same grams of MgBr2 to get to moles of the MgBr2, but now I don't want to go to moles of magnesium, I need to go to my moles of bromide. For 1 mole of MgBr2, now we have 2 bromides for each MgBr2 piece. Means we're going to need our 2 moles of Br minus up top there. So when we go ahead and solve this one out now, we're going to end up with 0.5220 moles of Br minus. One thing to notice about this is just double our moles of magnesium ions, which should make sense considering we have MgBr2. We have 2 times as much bromide as we have magnesium in that compound. So we see that here. So that could be a shortcut for you as you're going through and solving this problem. So now we need to go back up and add that mole value into our molarity equation for our bromide. And we should find that we have 0.652 molar bromide ions. Again, we should see that molarity between our Mg2 plus and our Br minus doubling because we have twice as many in that MgBr2. So be sure to be on the lookout for those relationships as well. So let's move on and look at part B. On part B, we want to know how many bromide ions are found in this solution. Well, what do we know about bromide ions so far? I know that I have 0.520 moles of bromide ions, and I know my bromide ion molarity. Well, if I'm trying to get to how many ions, how many particles, I'm going to want to start with that mole value. Then converting to moles to particles, well, that's just Avogadro's number. We know that every 1 mole of Br minus, or 1 mole of anything, contains Avogadro's number of particles. So once we multiply by Avogadro's number there, keeping our 4 sig figs, we should find our total ions of Br minus in that solution. So lastly, on part 3, we want to know the fraction of the total number of ions are bromide ions. Well, there are lots of ways to do this because we have the moles of each, we have the molarity of each, but it's so much simpler than that. All we need to go and do is look at that MgBr2 formula. Within this MgBr2 formula, we can find how many of each ion we have, and we can find the total number of ions in a formula unit. Well, if we're looking for the fraction of the total number of ions of bromide ion, we're going to need our number of bromide ions over the total ions. So it's that part over whole concept. Well, the number of bromide ions is 2. We have 2 bromide ions per MgBr2. And we need that over our total number of ions in MgBr2. Well, in this MgBr2, we have 1 magnesium and 2 bromides that make up the whole entire compound. So that fraction that we're going to have there is 2/3. 2/3 of all the ions that we have are bromide ions based off of this formula. So we do need to be comfortable with going, as we saw throughout this whole example, from a compound to the things within it, the ions within it, and incorporating that molarity equation. So we do have one more example, number 4. So again, try this out on your own and then continue the video and we'll take a look at the solution. So on number 4 here, we want to know how many hydroxide ions are contained in 2.5 liters of a 0.52 molar aluminum hydroxide solution. Well, if I'm looking for how many particles or how many OH minus ions, I'm going to need to figure out how many moles of OH minus ions. Well, right now, with my volume and molarity here, I can find moles of aluminum hydroxide. Our molarity equation is moles over liters. I have molarity, I have liters, so I can solve for moles. That's just going to be some simple cross multiplication here. Molarity times liters will always give us something that I would just keep in mind. We'll be doing that a lot. So on this problem, I'm going to take my molarity times my liters to find my moles. So that tells me I have 1.3 moles of aluminum hydroxide. Well, again, this problem is only asking me about the hydroxide. So we're going to need a little mole ratio here to break that down. Every 1 aluminum hydroxide is going to contain 3 moles of OH minus. I'm just getting that from the formula because every 1 AlOH3 has 3 OH minuses. But it didn't ask us the moles of OH minus, it asked us how many individual ones. So again, we're going to need to multiply by Avogadro's number here. Upon multiplying by Avogadro's number, we should find that we have 2.3 times 10 to the 23rd OH minus ions present in that solution. We do only get 2 sig figs, so this 1.3, 2.5, all those guys only had 2 sig figs. Okay, so there's a little bit of mole conversions using that molarity and these little mole ratios from the chemical formulas. So you'll get some more practice over the next few days, but let us know if you have any questions.